Okay, great. Hi, everyone. I guess everyone could hear me. Cool. So thanks for joining the LMC's office hour. I'm Mick from SGLang, and I'll be your host today. Well, it has been roughly 3 months since we first put out SGLang-Diffusion. The engine has evolved quite a bit since then, but we haven't actually done an online session like this before, so we thought it would be a good time to catch up and share what's been going on. Today is really about sharing some recent updates on what it takes for SGLang-Diffusion to be production ready. And we've got two guest speakers lined up. And last, I will share a quick community update at the end. Meanwhile, please feel free to drop any questions or thoughts in the chat or in Slack afterwards. So our first guest is developer from SII OpenMOSS team. If you haven't seen it, OpenMOSS is doing some brilliant work. They have released MoVA, a high-fidelity audio and video diffusion model. Today, they're here to talk a bit about the model's architecture and how they're integrated into SGLang-Diffusion. So right now, without further ado, here's CloudRipple. Let's welcome.
Hello. Could you shift my... Okay, let's begin. Hello, everyone. So, without further ado, Hello, everyone. I am Zhang Yang, aka CloudRipple, a PhD student from OpenMOSS team, Shanghai Innovation Institute, and Fudan University. It is a great honor to be invited by the SGLang community today to share our latest audio-visual generation model, MoVA. So, without further ado, let's dive into MoVA. MoVA stands for MoS Video and Audio. Our team is the same one that developed the MoS large language model, but recently we've shifted our focus toward multimodality. This new model is called MoVA because it can simultaneously generate both video and audio. One of its core strengths is supporting multi-speaker audio-visual generation. For example, it can produce content in both Chinese and English, where the speech is decoupled from the specific character, or while maintaining perfect lip sync. While we didn't specifically set out to enhance its text rendering capabilities, you can still get some really solid results just by rolling for the right cases. On top of that, MoVA is also capable of generating realistic physical sound effects to match the scene. Here is a demo generated by MoVA 360p. What you're seeing is a compilation of several top-performing cases we've picked out.
Let's make something really bad.
Yes! Let's tear it all down! Want to have some fried chicken?
其实我一直都在等一个人。
你一旦多活了一天，你就少活了一天。
每个东西上面都有一个日子。
You play with fire, you get melted.
Next, I'll walk you through our model architecture. For the architecture, we utilize an asymmetric dual-tower diffusion transformer, combining a compact pre-trained audio tower with a larger-scale video tower. Specifically, the video tower is a 28B parameter model with 14B active. In contrast, the audio tower is 1.3B parameters. We use bidirectional cross-attention across the first 30 90 blocks to handle modality fusion. You might wonder why we chose a smaller parameter scale for the audio component. Many of our team members come from extensive backgrounds in audio and speech processing. From our experience, while text and video require massive models to capture their complexity, a 1.3 bit scale is actually the sweet spot for audio. It is highly effective and more than sufficient for high-quality generation. A critical factor for audio-visual generation is the representation space. For the visual component, we utilize the 2.1 VAE. While it delivers impressive quality, its main drawback is the significantly long sequence length, which leads to substantial computational overhead during inference. On the audio side, after extensive research, we opted for the DAC VAE, the same one used in Hunyuan Video Foley, to achieve a more efficient and effective latent representation. For multimodal interaction, a critical step is achieving precise temporal alignment within the positional embeddings. Since the audio sampling rate is significantly higher than that of the video, sparse video frames and dense audio frames naturally exist on different temporal grids. Consequently, a naive positional indexing approach would cause tokens representing the same physical time to mismatch, leading to a temporal drift between sound and vision. To resolve this, we modified the indexing mechanism to unify the timeline. By introducing a scaling factor that reflects the ratio between audio and video frame rates, we scale up the video positional indices to align them perfectly with the audio timeline. Now moving on to data engineering. Our core objective here is to transform cluttered raw internet data into high-quality, audiovisually aligned training pairs, complete with detailed semantic captions. This pipeline is divided into 3 rigorous stages: video preprocessing, audiovisual quality assessment, and audiovisual captioning. By the end of this process, we filter out the noise and retain only a small elite fraction of the original data for training. In terms of data collection, we created high-quality subsets from several prominent public datasets, which were further supplemented by a vast volume of internal data. By ensuring a high diversity in our data distribution, spanning various domains and formats, we significantly enhanced the model's generalization capabilities across complex real-world scenarios. For video preprocessing, we developed a scalable pipeline built on the ray-distributed framework. The primary objective here is to standardize the core visual content, identify speech segments through VAD, and detect scene transitions. This process ultimately partitions the raw data into uniform, fixed-length clips ready for the next stage. Next, we move to audiovisual quality assessment. We evaluate our data across 3 core dimensions: audio quality, video quality, and audiovisual alignment. The table shown here outlines the specific metrics and filtering thresholds we've established for each dimension to ensure data integrity. The third stage is audiovisual captioning, where the goal is to provide semantically rich textual descriptions for the video data. We begin by generating separate annotations for audio and video, then use a large language model to fuse these inputs. This is followed by a cross-model consistency check, where the model validates whether the visual scenes and audio events are truly aligned, ultimately outputting a unified natural language description. Because the inference demand for this stage is massive, we deployed our inference engine across every available card in the cluster to handle large-scale labeling. There's actually a small story behind this. Initially, our algorithm team used VLLM, but they ran into significant efficiency bottlenecks and had to apply numerous internal patches. Later, our infra team recommended switching to SGLang, which immediately resolved the utilization issues and dramatically improved our throughput. That concludes the overview of our data processing pipeline. As a result of this rigorous filtering process, the final data retention rate was only 26.39%. Okay, let's talk about our training strategy. Stage 1 focuses on the independent pre-training of the audio tower. We developed a 1.3b parameter text-to-audio DT model with a dataset encompassing 3 primary categories: music, general sound effects, and TTS speech. Here are the audio tower evaluation results. Following that is the progressive joint training stage, which is divided into 3 main phases. We began with a 360p baseline training, starting from the pre-train 1 to 0.2 and audio tower models, while incorporating a randomly initialized bridge module. This was followed by a quality-footed alignment phase, where we trained on a higher quality data subset. Finally, we concluded the process with a 720p fine-tuning stage to achieve high-resolution output. Here's an overview of our training pipeline. Okay, finally, we've arrived at the inference and SGLang-Diffusion support section. Let's talk about our cold start phase for SGLang-Diffusion support. The timeline between starting this integration and our open source deadline was incredibly tight. To move as fast as possible, we leveraged codecs to automatically translate our native code into an initial SGLang implementation. Admittedly, this first version was far from optimized. It had quite a bit of computational redundancy and some unconventional coding patterns. However, it served its primary purpose, giving us a fully functional baseline that we could immediately run and begin refining under pressure. After the code stopped, we moved into a deep refactoring phase to turn that prototype into a production-ready system. We standardized our component loaders and consolidated our configuration and sampling classes to ensure high code reusability. The most critical engineering work, however, was in the model architecture itself. We refactored both the video DIT and audio DIT backbones to support tensor parallelism, and we overhauled the denoising stage to enable sequence parallelism and torch compile optimization. These changes were essential for scaling our inference across the cluster while maintaining the performance levels required for our open source release. In the process of refactoring video.it and the denoising stage for parallel acceleration, numerical fluctuations are inevitable due to changes in underlying operator implementations and parallel partitioning strategies. To ensure the refactored model faithfully reproduces the original generation effects, we established an automated regression testing framework. We quantitatively evaluate these discrepancies by comparing the video PSNR and audio APSNR of samples generated before and after the refactoring. Generally, maintaining these metrics at a high level indicates that pixel level and waveform level differences are minimal, virtually imperceptible to the human eye or ear, which validates the correctness of our parallel reconstruction. The technical logic involves using FFmpeg to extract and compute the signals between the two outputs. This framework allows us to quickly verify during every code iteration that the performance gains from parallel acceleration do not come at the cost of generation quality. On the right side of the slide, you can see a dataset comparing the results of the non-parallelized native implementation against various parallel configurations. Thanks to the incredible collaboration between our team and the SGLang community, we've successfully achieved day zero support for the MoVA model. The results are already impressive even at this early stage. Our implementation's inference speed surpasses the original native version. More importantly, by leveraging tensor parallelism to optimize memory usage, we've made it possible to run these heavy models on consumer-grade hardware like the RTX 4090. Of course, we're just getting started. Since the initial push was quite fast, we're currently cleaning up the code base and will soon contribute additional support for CFG parallelism, KJ-DIT, and layer-wise offload to further push the boundaries of performance. In addition, I'd highly recommend checking out our OpenMOSS multimodal series. These are all high-performance production-grade models that we are very proud of. And with that, I'd like to wrap up today's presentation. Thank you all for your time and attention. Now, I have one last secret to share. The voice you've been hearing this whole time wasn't mine. Every word of this narration was actually synthesized by our MoSS TTS model. Finally, none of these models would be possible without a rock-solid foundation. We are placing a huge emphasis on the infra side of things. If you are passionate about infra and want to build the next generation of production-grade models like MoSS TTS, we'd love to have you join us. Let's push the boundaries of AI infrastructure together. Thank you. Okay, that's all.
Okay, cheers for that. It's really great to see open source models pushing video generation forward like this. And yes, do we have any questions regarding OpenMOSS or MoVA? Great. Okay, let's move on to next speaker, I guess. Okay, great. Right, and our next speaker is from Skywork AI, also a contributor to SGLang-Diffusion. He has been spending a lot of time on accelerating the engine. Then today, he is going to walk us through some of the recent optimizations they've added to SGLang-Diffusion. So please join me in welcoming Xingyu Wang from Skywork AI. Stage is yours, Xingyu Wang.
Hello everyone, I'm Xingyu Wang from Skywork AI and the SGLang-Diffusion team. Today, I'm excited to share our recent work on optimizations for 1.2 video generation. Before diving into the technical details, let me introduce the background of our work. Our primary goal was to achieve efficient production-ready deployment of 1.2 on 8 Hopper 100 GPUs. We observed 3 interesting key points. First, in terms of parallel mode, Ulysses sequence parallel outperforms tensor parallel, but it can't reduce static memory footprint. Second, because layer-wide offloading can't be used simultaneously with cache DIT, and to avoid additional overhead, we should disable all offloading configurations. Third, under these 2 constraints, that is, using sequence parallel without any offloading, the original implementation of SGLang-Diffusion would simply run out of memory on 8 Hopper 100 GPUs. Therefore, reducing memory usage and improving efficiency are equally critical goals. To address these challenges, we implemented 5 key improvements throughout the entire inference pipeline. First, we implemented the token-level sequence sharding for DIT and an optimization we call parallel folding for test encoder. Second, we developed the parallel VE encoding and decoding to eliminate the memory bottleneck when processing high-resolution videos. Third, we fixed the critical bugs in cache DIT integration to enable stable dynamic multi-request serving. Fourth, we accelerated video save operations by eliminating some unnecessary overhead. Fifth, we developed custom JIT kernels for when we use specialized layer norm operations. Now, let me provide a detailed introduction to these optimizations. Our first optimization addresses sequence parallel sharding. In video DIT models, input tensors have the shape BTHWC that's batch, frame, height, width, and channels. For a typical configuration, the frame might be 21. Previously, we used frame-level sharding, which means directly sharding along the frame dimension. But the problem is, dividing 21 frames by 8 GPUs is not an integer. Therefore, we must adjust the frame to 24, which will introduce 14.3% redundant computation. Note that each field token needs to go through the HW and C dimensions. Our new approach is token-level sharding. Instead of sharding along T, we first flatten T, H, and W into a single sequence dimension, then shard along Z. This has two major benefits. First, H times W is often divisible by 8 for common resolutions, so we can achieve zero padding in many cases. Second, even when padding is needed, the overhead is minimal compared to frame-level padding. Looking at the comparison table, with frame-level sharding, we had 3 padding frames, resulting in a peer rank shape of 3 HWC and 4 feature map communication volume. With token-level sharding, we achieve 0 padding, a peer rank shape of 2.625 HWC and only 87.5% of the communication volume. This optimization delivers fast communication and reduces calculations and memory footprint, which is especially beneficial for long video sequence. Our second optimization is what we call parallel folding. Previously, the test encoder and the DIT shared the same tensor parallel group. When DIT only uses sequence parallel, the test encoder runs with TP equal to 1, due to each GPU storing a complete copy of the test encoder model. It results in memory waste and duplicate calculations. But the key is that the execution of the test encoder and the DIT is completely decoupled. They don't need to share the same parallel strategy. With parallel folding, the test encoder now uses the DIT's sequence parallel group as its own tensor parallel group. This means for a test encoder, we apply tensor parallel across the sequence parallel group, maximizing speed and minimizing memory. For a DIT module, we apply sequence parallel for optimizing the throughput for sequence processing. Both components now use their optimal parallel strategy without interfering with each other, maximizing overall efficiency. This is a simple but powerful optimization that gave us significant resource savings. The third optimization addresses a major bottleneck, VE encoding and decoding. VE involves heavy 3D convolution operations, and for high-resolution video, single GPU implementations are slow and prone to auto-memory issues. There are 2 common approaches to address this. Option A is tiling, where we split feature maps into tiles and process them sequentially. This reduces peak memory, but increases latency because tiles are processed one after another. Option B is parallel VE, which is our approach. We distribute tiles across GPUs for parallel processing, reducing both peak memory and latency. Our implementation for 1VAE uses a 3-step strategy. First, head-wide sharding. We split feature maps along the height dimension across all ranks. Second, halo exchange. During convolution operations, we use peer-to-peer communication to share boundary pixels between neighboring ranks. This ensures mathematical equivalence with global convolution. Third, alligator reassembly. During attention operations, we use alligator for global context. At the end of encoding or decoding, we use alligator to reconstruct the full height dimension. This approach completely eliminates VE as a bottleneck, enabling higher resolutions and longer sequence without auto memory. Our fourth optimization fixes critical bugs in cache-DIT integration. Cache-DIT accelerates inference by caching residuals and skipping some computations. However, its correct execution depends on proper non-inference steps configuration. We discovered 2 critical bugs in original implementation. First bug was wrong steps configuration. 1.2 uses a dual transform architecture. Transformer 1 runs normal high noise steps and Transformer 2 runs normal low noise steps, which together sum to normal inference steps. Both transformers were incorrectly using the total normal inference steps to initialize their cache context. Second bug was cache contamination across requests. In serving mode, cache content is persistent across requests. When different requests use different normal inference steps or different video shapes, this caused cache buffer shape mismatches, which would crash the server. Our fixes address both issues. First, we configure independent cache contexts for transformer 1 using normal high noise steps and transformer 2 using normal low noise steps. Second, for each new request, we recalculate the time step splits and refresh cache context using cache DS interface. This completely isolates requests from each other. These fixes ensure stable production-ready serving with cache DIT acceleration. Our fifth optimization touches the video saving pipeline. Previously, the workflow was GPU worker completes inference, serializes the output tensor, sends it to scheduler client via XMQ. Then scheduler client deserializes the tensor, processes it, and saves the video. This introduced a significant overhead from serialization and deserialization, plus duplicate tensor copies. Our solution is simple but effective. GPU worker now directly processes the output tensor and saves the video to disk, retaining only the file path to scheduler client. This limits serialization and deserialization overhead entirely, while avoiding duplicate tensor copies. It's a straightforward optimization that makes a noticeable difference in end-to-end latency. Our final optimization addresses one video's specialized layer norm patterns. Pattern 1 is layer norm scale shift, and pattern 2 is scale residual layer norm scale shift. Implementing them as separate kernels introduces multiple kernel launches and intermittent memory traffic, creating GPU bubbles. Therefore, we use Qt DSL to implement fused JIT kernels that combine these operations into single efficient kernels. The benefits are threefold. First, fewer kernel launches, reducing launch overhead and CPU-GPU synchronization. Second, lower memory traffic, eliminating intermediate memory accesses. Third, better GPU utilization, reducing bubbles and improving overall throughput. Now, let's look at the performance results. This chart compares SGLang-Diffusion against the LightX2V for 1.2 text-to-video generation. Our optimal implementation latency is about 47 seconds, while LightX2V is about 80 seconds. In addition, we have lower peak memory usage. Although this result was measured on the Hopper 200 GPUs, but SGLang-Diffusion's optimal configuration can run on Hopper 100 GPUs without any performance loss. That's to say, although peak memory only includes touch memory, even with CUDA memory and Nickel memory added, 8 GB of memory is still sufficient for SGLang-Diffusion. That concludes my presentation. Thanks for listening.
Thanks Xingyu so much for the run-through. Performance is essentially a never-ending job, and we will keep pushing the limits on diffusion generation. Yes? Okay. Right, moving on. Well, since we just had a Lunar New Year, we're actually running a community event at the moment called SGLang. It's basically a creation contest. You can make anything, including images, videos, 3D models, as long as it features the mascot, the SGL girl. There are two tracks, a general one and a specific one for SGLang-Diffusion. And we have got some quite nice prizes. Yes, we are giving out free Cursor Pro subscriptions, some custom merch, and a chance to have your work featured at SGLang-Diffusion future offline meetups. It's open until the 3rd of March, so please join if you're interested. Next, I'm quickly sharing some recent updates on project, and then I will do a quick QA session on the previous comments in the chat. Yes. I have put some useful links on the slide, the repo, the 2026 Q1 roadmap, and the blog posts we have made since launched. If you're interested in what's coming up or want to pick something up, do leave a comment, take over in an issue, or just simply find us at Slack. And yes, I will quickly run through the chat, the questions raised. So I see someone asked, could you tell me more about the parallelism? Yes. Typically, we apply tensor parallelism for text encoding stage since the bottle size are relatively large for text encoders. And for denoising stages, we typically apply a sequence parallelism or context parallelism, which is basically a Ulysses or ring attention, to mitigate the high VRAM usage of the activations. Yes, that's the parallelism used in SGLang-Diffusion mostly. And I saw another question: would something like block diffusion be relatively efficient to serve on SGLang? I assume some sort of flex attention was used for this model. Yes, I think you are referring to diffusion language model by block diffusion, and SGLang-Diffusion is currently focused on visual output denoising generations. And in SGLang main repo, we do support DLM, and please remember to check that out. And regarding the flex attention, yes, we could implement a dedicated attention backend for flex if that's ideal for us and the performance is great for flex attention. We could implement any attention backend we want. Yes. Any other questions? Okay, cool. One more thing to mention is that, okay, yes, you could check the DLM work by SGLang. Thank you. One more thing is that we are giving out SGLang GTC tickets, and we are giving away 20 of them as a 4-day exhibit passes. Each will worth a lot of money. Yes. If you are interested, please follow CS.org on X, Twitter, SGLang or GitHub, and share your favorite open model. Yes. Well, that's pretty much it for today. And a massive thanks to our speakers for taking the time to share, and thanks to all of you for tuning in. If you are building things with SGLang-Diffusion, whether inference or training, definitely reach out. We're always around on Slack. If you fancy a chat, want to open a PR, or just drop some feedback. And cheers, everyone. Enjoy the music and have a good one. See you next time.
是爱。